which is going to be under intermolecular forces. So we'll talk about IMF. Yeah, so this is, so today we'll look at part 1. So intermolecular forces, these are simply types of attractions that are going to be found within, or rather between, molecules. It can be within or between molecules. So we have what we call intermolecular forces, and we have what we call intramolecular forces. So inter just means like what you used to have. Let's say you have what do you call that? Inter-schools sports, right? Meaning it's between different schools. Intra, it's simply going to mean within the same molecule, sort of. Yeah, so when we say within, we mean things like cohesion. That's an example of an intramolecular force. About intermolecular forces, we mean forces like hydrogen bonds. So here we have things like hydrogen bonds. And also, apart from hydrogen bonds, we can talk about covalent bonds. These are also intermolecular forces. Then apart from this, we can have ionic. So anything between molecules, ionic bonding. So we just started, we're saying we have intermolecular forces and intramolecular forces. Intra means within the molecule. A perfect illustration is cohesion. Then inter, we have forces between different species or different molecules, and these are some of the examples that we'll be discussing. Yeah, so the ones that we're going to be mostly interested in are hydrogen bonding. So the types, so let me just show you the forces we're going to look at. So these are things that you've done in biology already. It's just kind of a revision. So hydrogen bonds. So what's a hydrogen bond, guys? What's a hydrogen bond? Anyone who remembers this? A hydrogen bond, so that's true, Ted. A hydrogen bond is simply a bond that is formed between a hydrogen atom in a molecule and another electronegative atom in another molecule. More specifically, we talk about fluorine, oxygen, and nitrogen. That's when a hydrogen bond is formed. They have to be in different places. So if you have hydrogen and let's say fluorine, this hydrogen and this oxygen can form a bond, a form of attraction. And this type of attraction is mainly going to be caused because of the dipole moments that are going to exist on the individual molecules. In water, you know there's a negative this side, there's a negative this side, there's a positive, there's a positive. The reason why oxygen is carrying a negative because it's more electronegative than hydrogen. Same applies here. This will be positive, then this will be negative. So you are seeing this guy and that guy. So this is a typical illustration of a hydrogen bond. The other type of bond they are going to be asking you about is a covalent bond. So a covalent bond, you know when it's formed, it's between a non-metal and a metal, right? Equal sharing of electrons. And whenever this forms, we're going to be demarcating covalent bonds into two types. It's either your covalent bond is polar or your covalent bond is non-polar. So the polarity or the polarization of your molecule depends on whether that molecule has charges or not. Does it have dipole moments? Right? That's what we're interested in finding out. So if I give us something like, they gave us something like this from the Chem 1010 tutorial sheet. There was this question here, question number 4. They were saying, what types of intermolecular force exist between the following molecules? This guy that you have here, the first one. So on question 4, the first thing we needed to write is the Lewis structures. If possible, we have to look at the Lewis structures. So when they mean intermolecular forces, we're looking for forces between these two molecules that have been given, right? Remember we've said we have inter and intramolecular forces. That's what we're looking for. So they want us to examine all the possible intermolecular forces. So here I must also add, we have ion dipole moments. These are also part of intermolecular forces. And we have something that we can have. We have dipole induced as well, so we can say dipole induced. And also apart from this, I can also add, we say we have van der Waals, or we can say London dispersion forces. We can call them this. This is the LDF, the London dispersion forces. Yeah, so these are the types of intermolecular forces we can always look for. So if you look at the two molecules that I'm trying to make us observe, we have this guy here. We have the hydrogen bromide. So we have HB. This is what we're having, HBr, and we have hydrogen sulfide this side. So this is just going to be something that looks like that, and this here is going to be S. There's a hydrogen, there's a hydrogen. This is going to give us the same behavior like water, because S is having 6 electrons in the outermost shell. So if you think about it, you're having hydrogen to bromine, this guy here, and you're having S with a hydrogen and a hydrogen with the 2 lone pairs there. So you're going to have negative there, positive, negative there, then positive, then you're having a negative, then this is positive. Because bromine is a halogen, meaning it's more electronegative than hydrogen. So this makes hydrogen bromide to be a polar molecule. So we have this. We can first of all write this. These two molecules are polar. So if they are put in close proximity, you're going to experience London dispersion forces. These are a must. Everything, whenever you put two things closer to each other, there's going to be some form of attraction between those two things. That's what we call the London dispersion forces. That's the LDF. Then the other type of force you're going to experience here will be a dipole to dipole, because the positive can attract the negative there. The positive can be attracted to that. So you can have dipole to dipole interactions. Someone else may argue to say you can also have a hydrogen bond, but then hydrogen bond is only mostly considered when you have something that's very electronegative, like fluorine, oxygen, or nitrogen. So these are the only two prominent type of intermolecular forces that you can have between these two molecules that were given. So all I'm saying, guys, that this topic talks about the forces of attraction. That's what we call intermolecular forces. What forces are always present whenever things are bonding or things are given? They can be separate from each other, like how this question was given. How can this guy be related to that guy? What type of bonds can be formed? The possible ones, right? So we study each particular molecule separately. So we figure that this guy is polar because the electronegative here is going to give us partial charges, because bromine is very electronegative as compared to hydrogen. The same applies this side. This is just going to be like the molecule for water, because sulfur and oxygen are in the same in the same period. Yeah, so this is how you identify your intermolecular forces. Now, away from that, I want to emphasize on how you can tell whether something is going to be dipole to dipole. Dipole to dipole only exists if there is a marginal difference in the electronegativity values, which is mostly going to be given. So under chemical bonding, they were giving you, they will tell you to say the electronegativity of hydrogen is, let's say, 0.3, nitrogen is, let's say, 0.7, let's say something else, let me put oxygen, is, let's say, 1.2, fluorine, the most electronegative one, 1.7. So if I ask you to say which one is more electronegative between the following bonds, so you have to find the differences in the expressions given. So like this one here, hydrogen and fluorine, what's the difference? The big one minus the smaller one, that gives us 1.4. nitrogen and hydrogen. So this is going to give us a 0.4, hydrogen and oxygen. So this is going to simply give us 0.9. Fluorine and oxygen, this is going to give us a 0.5. So look at what you're having. The one that has a bigger electronegativity difference is the one that's very polar. So this is polar, and we'll have more charges, followed by this one, then followed by that one. Then this guy here is non-polar, and it will be the least to form any charges if it ever forms. So the electronegativity has to be greater than 0.5 for something to be polar. So they'll always give you something like this if they want you to get a descending order of this. So we're saying this is stronger, followed by this, followed by hydrogen and oxygen, then followed by nitrogen to hydrogen. Now, why are we learning these forces? We're learning these forces because we want to talk about how we can convert things from solid, liquid to gas. Remember the states of matter that you learned in high school? That curve that you are learning, that if you hit something that's a solid, if this is a solid, when you hit something, you're going to see a mixture of a solid and a liquid when it's melting, right? When it's completely a liquid, we call that to be the melting point. Then it has to boil up. Then when everything becomes vapor, meaning that's the evaporation point, we'll see something like this. The heat curve, remember that heat curve? That's what we're interested in. So we are learning the bonds that we're supposed to break for us to have any reaction that we'll need. So we are saying this is melting. If you're moving from solid to liquid, that's melting. From liquid to gas, what do we call it, guys? This is evaporation here. So please stay with me, guys, here. I'm just trying to make this very simple for you. So we're coming from a history where we're discussing bonds, right? The bonds that are found in these molecules will be melting and evaporating. So this is condensation. Then here, liquid to this is just freezing. Then what's the process that we use to convert something from a solid directly into a gas? What do we call it, guys?
Sublimation.
This is sublimation. Then how about a gas back to a solid? What do we call it?
Deposition.
Correct. That's deposition, yes. That's very good, Teddy. So this is deposition. And we're saying these things are going to be having those forces, keeping them together. So you already know the state of matter. When you talk about what's the difference between a solid and a gas, you know, right? Or a solid and a liquid. You know those things like a solid has a fixed shape, fixed volume. The vibrations are minimal. There is completely zero or no movement or whatsoever. Then liquid, you know. Gas, you know, these are compressible, those things, those properties, right, of liquids and solids and everything. Now, the most important thing that we're going to discuss is the ability of us to convert these from one thing to another, and we're going to use what we call phase diagrams to analyze the conversions that we're going to be discussing. So whenever we discuss a phase diagram, we just mean a diagram that relates. We are from looking at the forces. Now we just want to talk about the conversions, and this is the type of diagrams we're going to be calling phase diagrams. They're just going to be helping us to learn how to discuss what needs to be done for us to convert something from a solid, liquid, or gas. So here you have a solid, here you have liquid, here you have a gas. This point here is what we call the triple point. This is a point where all the three states of matter coexist. So this is what we call the triple point. Then we have this point here. This point here is what we call the supercritical point. Because once you bypass this point, what you're going to get here is a supercritical fluid, which is an ideal fluid, which is neither affected by the changes in the temperature or rather the pressure. So this is a solid, right? Then it can be converted into a liquid. So look at what is happening here. We're relating pressure to temperature. So we're saying if something is at this point, imagine I give you a solid at this point, which has this pressure, the pressure at this level here. So what do I need to do to this solid to make it to be a gas, for instance? I can keep the pressure constant and increase the temperature continuously. This thing will move here and it will become a what? Directly, you have sublimation, it becomes a gas. So this is what a phase diagram is all about. So if you have something here which is a liquid, let me put it in blue here. Let me show you to say if you have, if this guy is a liquid there, I want to convert this into a gas. I'll keep the pressure constant and, I'll keep the temperature constant and reduce the pressure down, meaning a liquid can be converted into a gas by maintaining its temperature and decreasing the pressure. That's basically what we are saying. Anything here, this is the critical point. Yeah, so this is also called just the critical point. We just say critical point, the CP, because anything after this point is, if it was a gas, it will continue being a gas. If it's a liquid, it's going to be a liquid. Yeah, so this is what we mean by phase diagram. Now we have two types of phase diagrams that they're going to be interested in. There's one for carbon dioxide and there's one for water. The difference is in the placement of the 1 atm, 1 atmospheric pressure, where it's going to be located. That's how you tell to say this is for carbon dioxide and this is for water. So let me give you the one for water, so that you can, once you know the one for water, you'll be able to tell the one of carbon dioxide. So yeah, so the one for water, the 1 atm is above the triple point. So if I give you the phase diagram for water, it looks like this. So you have something like that. So 1 atm is somewhere here, 1 atm is above. So we have something like this. The triple point is there, the critical point is there. So this is what you have. They don't show this, they just show it like that. Then the one for carbon dioxide, so this is what I mean. 1 atm is somewhere here. It's down below the triple point. So that's how you differentiate them. They only ask about these two guys. But you don't even have to memorize this because they'll give you the diagram, right? Then you have to just extract information based on the diagram they're going to give you. So I'm going to have question number 5 from the chemistry 1010 tutorial sheet 8 as an example. So this is going to be example 2. Let's call it example 2 from the previous illustration we're from having. So they are saying phase diagrams are used to depict changes in the properties of a solution at different temperatures and pressures. Then they are saying below is a phase diagram for a polar solution. So meaning it's a solution and it's polar, meaning it dissolved in water, right? The first question here that they're asking is, what processes are occurring at point Q? So point Q is a triple point, right? So you just say point P, you're explaining. So we say point Q is a triple point, and all the states of matter are coexisting. So yeah, so there's instantaneous change. Some people say there's an instantaneous exchange between solid. Things are changing to solid, to liquid, and also back to gas. So this is what is happening. All the 3 states of matter are present at point Q. That's what you have. So this first explanation is enough for number 1. When they say what name is given to point R, so point R here is the critical point, that's your CP. Then they're saying define the critical temperature. So the critical temperature is the temperature at which all the 3 states of matter coexist. The same applies to the critical pressure. So this is called or this is critical temperature, right? So critical meaning here, okay, not triple point temperature, but critical temperature. So meaning the temperature where the critical fluid has been attained. So it's a temperature where the state of matter can no longer change. Once we reach that particular temperature, there's nothing that you can do to change the state of matter of whatsoever that you have. Yeah, then they are saying what name is given to a material at temperatures and pressure above those. So the name here is what they want is supercritical fluid. So we call it supercritical fluid. That's what we mean. Yeah, it's like it's a special fluid which is not affected by the changes in your temperature and your pressure. So that answers your number D. Is there anyone, guys, who is lost here? Any questions on the phase diagrams? Anyone who has a question?
Just defining question C for me again. Sorry, I didn't get what you said.
Or question C, when they say define the critical temperature, this is the temperature at the critical point where no changes are going to be observed in your state of matter. So your state of matter could be anything, right, at the critical point. All we are saying is that this is, just say the temperature at the critical point, that's all, because we already defined what a critical point is. You can say a critical point is a point where no changes are going to be observed or whatsoever in the state of matter that is existing at that particular point. So if it's a gas, it will continuously be a gas. Nothing is going to affect it. If it's a solid, it will continuously be a solid. But the only two possibilities, it's either something is a solid or a liquid. I mean a liquid or a gas, because solids are only found here, right? Solids are in this compartment. Then we have liquid there, then we have gases. Yeah, so no wonder we say it's an ideal supercritical fluid. It's just something that does not exist. Some people say no plasma, but then no. Plasma can actually be solidified, so it disqualifies as that. We just believe that there's a temperature at a certain point where nothing happens to whatsoever that you have. It will continuously be what it is. Yeah, so I don't know if that answers your question, Ted. The answer here is just, it's the temperature at the critical point. Is that okay?
Yes, it's understood.
Yeah, then look at the next example. This is a typical illustration. So from what I gave you, remember we said there is only for carbon dioxide and water, right? So this here is on carbon dioxide. You are seeing the 1 atmosphere is below the what? The triple point. That's what you have. This is the standard exam question they can bring when it comes to phase diagrams. So based on the phase diagram of carbon dioxide below, answer the following questions. So we're just going to be picking answers from this. Know that this is one of the nicest topics that if you get things wrong, meaning you just have a problem, because it's just picking things from there. At what temperature and pressure can the solid, liquid, and vapor phases of carbon dioxide coexist at equilibrium? So here the answer is here. They're asking about the triple point. Where can we see solid, liquid, and gas? It's the temperature. So the temperature that they're talking about at the triple point. So the triple point is just going to be negative 56.6 degrees Celsius. Then the pressure is 5.11 atm. This is the answer to question number 1. This is the triple point pressure and triple point temperature. Then number 2, they're saying, what is the effect of increase of pressure on the fusion and boiling of carbon dioxide? So if you put something here, so they're saying what is the effect of increase on pressure on the fusion and boiling of carbon dioxide. So if we put something here, for instance, so let's say something here, it's a vapor, right? Yeah, so if it's a vapor, imagine if we make temperature, or rather we can even use the triple point here. Keep your temperature constant. What happens to what you were given if we start increasing the pressure? Imagine we just increase the pressure. Your thing will become what? A solid. It solidifies. So the answer to this is it solidifies. So we're just interested in pressure. So meaning temperature has to be standardized. We have to keep it constant. Think about it like this, guys. We're just saying, imagine we keep the thing here, we keep the temperature at -56. What will happen to this thing if we increase the pressure? It will move and becomes a what? Becomes a solid. Yeah, so the answer here is that it solidifies. Then number 3, what are the critical temperature and pressure for carbon dioxide? What is their significance? So the critical is here, this guy here, right? That's the critical temperature, that's the critical pressure. So the significance is that we should not exceed them, because once you exceed them, you won't know what you have. You will no longer have carbon dioxide. Whatever you're going to have is just going to be a supercritical fluid. It's no longer going to be carbon dioxide. These are like the limits. They set a boundaries in terms of how far we can tamper with the pressure and the temperature. So that explains here. So you put your answer. Your answer here is that the temperature is 31.1 degrees Celsius and the pressure is a 73 atm. These are like the limits. That's what you have. Yeah, then number 4, the last one, they are saying, is carbon dioxide solid, liquid, or gas at -70 under 1 atm? So -70 is somewhere where -70 is so -70 is here, right? Because -70 is here under 1 atm. So under 1 atm is here. That's a limit of 1 atm. -70 is right here. So your thing will be a gas. The first answer here is that it will be a gas. For A, that's a gas. Then under -60, -60 under 10 atm. So -60, which is 2 in between here. So we're saying -60 under 10 atm. 10 atm is somewhere here, right? Somewhere there. So under 60 is there. So this thing could either be, you can say gas or solid. So we have 2 answers here for this one. If carbon dioxide is kept at -60 degrees under 10 atm, it can either exist as a gas or a what? Or a solid, depending on the pressure that you're having. Anything on this line, so this line that I've sketched here, so this is your 10 atmosphere here, 10 atm. Anything below, so meaning from -60 up to there, so it can be anything on this line. So that's only giving us 2 possibilities, solid or what? Or vapor. Yeah, so before I take any questions, look at number 15. Number C, they're saying, what is it going to be solid, liquid, or gas at 15 degrees under 56? So 15 degrees, let me erase this for you. So 15 degrees, so this is that, then this is going to be what? So we have a 0 somewhere there. So 15 degrees is somewhere there. Then under 56. So if you go there at 15, meaning they have 2 possibilities. It can either be what? A vapor or a liquid, because we are looking for anything under the 56. Yeah, so it can either be liquid or solid. Or gas, sorry. Yeah, so it will be liquid or gas. So for this one, we say vapor or liquid. Any questions, guys, here? Anyone who is lost here? This is one of the obvious calculation that also comes under section B, so your question 6. So aside from being able to identify the phases that we have, there's also a calculation that is relevant. We need this calculation because there are times when they'll give you 2 particular pressure values. So it's like the conditions in terms of pressure are no longer standardized. We're going to look at it from two particular pressures to determine how much heat of vaporization was needed. Right? This is just us trying to answer your question number 6. So they're saying the vapor pressure of this expression of a substance. So the initial pressure is 23 at this temperature. Calculate the vapor pressure at this if the enthalpy of vaporization is this. So we have a general standard equation which is almost similar to the Arrhenius equation on what is it? Is it kinetics or what topic was that? So there is this equation that we're going to be needing. So this equation only works if you have two pressure values and two temperature values to know how much heat is needed to vaporize something. And here we have 1 over T1 minus 1 over T2. This is the equation that we have. So this is called the Clausius-Clapeyron equation. So in this question that we are given, we have the initial pressure. So P1, we have it. P1 is 23. Then we have the initial temperature, which is 210. Then they're saying T2 is 415. K, this is K. We're looking for P2 when the heat of vaporization was given in kilojoules per mole, which is just the same as 28,000 joules per mole. This is the heat of vaporization. So we're just going to plug in everything that we need here. So according to what we've been given, we'll say lean. The pressure that we're looking for, we'll say P2, the initial pressure, which is simply 23 torr. Then this is equal to, we are having a 28,000. This is what you're having. Then down, I'm just going to use the expression that has no pressure units because the pressure units are going to remain here. We need this star, right, to be the units of P2 by the time we're done. So this is going to be 1 over the initial temperature, which is just 210, then minus 1 over 415. So we're solving for this value there. So this is going to be lean P2 over 23. Yeah, so if you do your calculation this side, you should be getting something like, if you punch everything, you get a 7.921. Then from here, we are changing this from natural log to exponential. So the base here is E, right? You've done logs now, so we're changing it. So E to the power this is equal to this guy. So P2 over 23 torr is equal to E to the power 7.921. From here, we're just saying P2 is the same as E 7.921 multiplying 23 torr. So this is just going to give us your final answer, which is going to be in torr, which is just the same as 63374, then point your 2 torr. So this was the second pressure at the temperature that was given. For us to achieve that particular heat of vaporization, this is the amount of pressure that was needed, or rather that was added. Any questions here, guys?